All right, this is part 8 of Unit 2, and we will be looking at logarithmic functions. Now, we've talked a little bit about inverses and we talked about exponential functions. Logarithms are the inverses of exponential functions. So we're going to convert back and forth between log form and exponential form. And then we're going to get an introduction to logarithmic rules, and then we're going to look at graphing logarithms. Now, if you think back to when we first in Unit 1 looked at exponential functions and we had all these exponential rules. We also have rules that we will be looking at for logarithms, and so that'll be kind of more tools added to our toolbox of if you think about things that we are allowed to do with these types of functions. So first off, logarithms. This is the form of a logarithmic equation here. We have what's called the base, the value we're taking the logarithm of, and a logarithm acts like a function. If you've ever been to like a pizza place or a restaurant where they have those little kid games that you put a quarter into and then you twist the handle and a little toy comes out of the bottom of it, that if you think of that box kind of like a function, and that quarter is what you're putting in, and then you're getting something out of it, and you're getting something different. It's not like you put in a quarter, you get out a quarter. You put in a quarter and you get something else out. So a logarithm works kind of like that machine, and you're putting something in it, and then you're getting something else out. That's what the logarithm will be equal to. And there's different kinds of machines. Well, there's different kinds of logarithms, and that's dependent on our base here. Now, there's a couple rules for the logarithms. What we're taking the log of has to be positive. It cannot equal 0, and it cannot be less than 0. Our base must be positive, so it must be greater than 0 as well, and the base cannot equal 1. So this is log form of an equation, and we can turn that into what's called exponential form. And the way you convert back and forth between logarithms, I call this and exponential functions, I call this the snail rule. This is not the technical term for it, but when I took Algebra 2 in high school, this is what my teacher called it, and it just kind of stuck, and I've called it the snail rule ever since. So if we have the base of our logarithm, and I draw a line to the other side, so b to the power of y is equal to what we're taking the log of. So you can convert back and forth between exponential form and log form. So if you have exponential form, you can go to log form. Whatever the base is of your exponent, that will be the base of your logarithm. And then the exponent on your base is on the other side of the equal sign. And then what it's equal to is what you're taking the log of. Now this next part here, we have all of our rules for logarithms. So if I have log base b of 1, regardless of what my base is, if my base is 5, 10, 7, doesn't matter, whatever my base is, if I'm taking the log of 1, that's equal to 0. That's kind of like our exponential rules, where if I have x to the power of 0, that's equal to 1. It's kind of the similar version of that for logarithms. Now, if I have log base b of b, if these two numbers are the same, then that's equal to 1. If I have log base b of b, again, these two numbers are the same, but this has a power on it, it will be equal to whatever that power is. And then if I have b, and then in the exponent I have a logarithm, and then the base of that logarithm is the same as this base, then that whole expression is just equal to whatever we were taking the logarithm of. Now, just like we have natural exponential functions with the e to the power of x was the natural exponential function, we also have natural logarithms. And rather than writing log, we write ln. That was what represents natural log. So natural log of 1 also equals 0. Same rule. And then the base of a natural logarithm, well, if you see ln of x, what that means is it's a log with a base of e. And so if the base and what we're taking the log of are the same, then it's equal to 1. If we have the base and that are the same and with an exponent, it's equal to the exponent. And then again, so this is just the natural logarithm version of each of these rules. We also have what are called common logarithms. Common logarithms, I'm going to kind of jump down here, are if we have a log base 10. And they're called common logarithms because they're really common. It's what we do a lot. So log base 10 of a logarithm, if you don't see a number there, you're assuming it's base 10. Okay. So ln x is the same thing as log base e. Log with no base is base 10. And then these are some more tools that we're going to be using here. So we'll come back to these probably in video part 9. And basically what logarithms do allow us to change multiplication to addition, and they allow us to change division into subtraction and exponents into multiplication. There's a couple of things here that are lined up poorly, so let me just kind of point those out real quick here. First off, this should have been over here. So what we're saying here is log b base b of m plus n. You can't separate that. It's not equal to this. Okay. Now this also formatted strange, so when I printed it, it didn't format correctly here, but that should be a little b. It should be a base for that little logarithm. All right. So we'll come back to these rules a little bit more in part 9, but they are here just kind of for your use. Now, these first couple examples we have here, what they're asking us to do are to use these rules that we saw up above here. So you're not going to be able to see them in my screen, but they're on the same page, so you have them in front of you. And you're going to be evaluating these using those rules. Now, the one we're going to use the most is this one. If I have log base b of b, meaning these two numbers are the same, then it's going to be equal to whatever my exponent is. So what we're going to try to do is rewrite these so that these numbers are the same. Well, I can start off this first one rewriting log base 3 of 81 as log base 3 of, and then 81 is 3 to the 4th power. Well, now these two numbers are equal, so this is equal to whatever my exponent is, in this case 4. The next one, log base 4 of 1 over 16. My goal is going to be to write 1 over 16 as 4 to some power. Well, I know for sure log base 4 of 1 over, and rather than writing 16, I can write 4 squared. It's not quite in the form I need it yet though, because this is a fraction and I just want 4 to some power. But I know I can move this up and make this 4 to the negative 2 power. So I can rewrite this as log base 4 of 4 to the negative 2 power. Again, negative 2 would move it to the bottom and make it positive, which is what we had here. Well, now that those numbers are the same, this is just equal to what my exponent is. Now this next one, if you recall back to our rules for square roots and rational exponents, if I have the square root of 5, I can rewrite that as 5 to the 1/2 power. And these numbers are the same, so this is just equal to my exponent. Now this next one, there's actually nothing we need to do. My base is e, this is e, those are the same, so it's equal to my exponent. Now this next one is harder. It's a little bit different of a question, and the fact that it's harder, it looks really similar to this first one, but here we have 3, and then 81 we could write as 3 to some power. 3 is smaller than 81. It's easier when your base is smaller than this. But here, this is larger than what I have here. So I kind of have to think backwards. I'm trying to think 16 to what power equals 2? Well, if it's getting smaller, then that's going to be a fraction or a rational exponent. So we want to be thinking, is it the square root of 16 that equals 2? No, it's not. Is it the cube root of 16 that equals 2? No, it's not. Is it the 4th root of 16 that equals 2? Yes, it is. So the 4th root of 16, we can rewrite that as 16 to the 1/4 power. So this right here, 2, again, that's equal to 2. So what I'm doing is replacing 2 with 16 to the 1/4 power. So log base 16 of 16 to the 1/4 power. Again, all I've done is replace 2 with 16 to the 1/4 power. We just said that that's true. Now these numbers are the same, so this is equal to my exponent. All right, and then the last one here. This will take a couple of steps here. So I see the 6 in there. There's a couple of things I want to do here. If I have log base 6 of 1 over, and the cube root of 6 is the same thing as 6 to the 1/3 power, but I want to move that up, so it's going to have to become negative log base 6 of 6 to the negative 1/3 power. Now these numbers are the same, so it's equal to that exponent. So that's how we can simplify logarithmic expressions. What we're going to look at now is graphing logarithms. So when we are graphing logarithms, when we do this the first time, we're going to be using exponential functions because we talked about that they are inverses of one another. Now back in the last video in part 7, we graphed this function. I'm just going to go ahead and make that table real quick. We did this exact example in that video, so if you need a refresher on it, you can go back to that video. But if we have -2, -1, 0, 1, and 2, 2 to the -2 is 1/4, 2 to the -1 is 1/2, 2 to the 0 is 1, 2 to the first power is 2, and 2 squared is 4. So I can go ahead and plot those points. And remember that we had a horizontal asymptote at the x-axis here. And it's getting infinitely close to that asymptote, but never actually touching it. So we had that horizontal asymptote of y equals 0, and then we had this as our graph. Now remember, with inverses, when we went over inverse equations, our domain and our range switch. So here, f of x equals 2 to the power of x. This function is the inverse of log base 2 of x. Again, base 2 here, and log of x, and then 2 to the power of x. These are inverses of one another. So what I can do is I can switch the domain and range. So my inputs become my outputs. And then these correspond 1/4, 1/2, 1, 2, and 4. And I can go ahead and plot those points now. That actually gives me a table of points to plot here. So plotting those points, 1/4, -2, 1/2, -1, 1, 0, 2, 1, and 4, 2. And that gives me my graph. Now, instead of having a horizontal asymptote, I have a vertical asymptote at the y-axis. That's x equals 0. So, from here, my graph continues to go up this way and then down this way. Remember, with logarithms, we can never plug in 0 or negative values, so it makes sense that we would have a vertical asymptote there because we can't plug in anything on this side. Okay. So, we don't always want to have to use an exponential function to draw our graphs. So let's make some observations about these x values here and the outputs here. If I was plugging in 1/4, well, log base 2 of 1/4, if we think about what we were just doing on the previous page, I could rewrite this as log base 2 of 1/2 squared, and then log base 2 of 2 to the -2 power. So this would be equal to -2, which is exactly what we get as our output. And we could follow these same rules again for 1/2, and I'd get -1. Plugging in 1, well, log base anything of 1 is equal to 0. Log base 2 of 2, if I plug in 2 and 2, those are the same number, so it would just be equal to 1. If I plugged in 4 here, 4 is the same thing as 2 squared, and so it would be equal to that exponent 2. We can do more values. I could do 1/8 and 8. And if I plug in 1/8, this is going to be equal to -3. Again, log base 2, and 1 over 8 is the same thing as 2 to the negative 3 power, so that's equal to negative 3. 8 would be positive 3. Again, 8 is the same thing as 2 to the 3rd power. So these values that we're getting here are based off of what our base is. So when my base was 2, I used 1/4, 1/2, 1, 2, and 4. In this next example, when my base is 3, I'm going to use 1/9, 1/3, 1, 3, and 9. And if I plug in 1/9, log base 3 of 1 over 9. Well, that's the same thing as log base 3 of 1 over 3 squared. Moving that up, log base 3 of 3 to the negative 2 power. So that's equal to negative 2. 1/3, log base 3 of 1/3. That's the same thing as log base 3 of 3 to the negative 1 power. That's equal to negative 1. Log base 3 of 1, well, log base anything of 1 is equal to 0. Log base 3 of 3, well, if those two numbers are the same, it's equal to 1. Log base 3 of 9, that's the same thing as log base 3 of 3 squared, so that's equal to 2. And now we have this set of points that we can plot. So 1/9, negative 2, 1/3, negative 1, 1, 0, 3, 1, and 9, 2. And that gives me my graph. And again, I have that vertical asymptote. You need to make sure you graph every single time. And that is my graph of this function without using the exponential function to help get those points. Now, just like we saw with exponential functions, I started out using 5 points and eventually went down to using just 3 points. If I was graphing this function, I could use whatever 3 points I want. So I like using 1/3, 1, and 3 and getting negative 1, 0, and 1. You could also use 1, 3, and 9 and then you get 0, 1, and 2. You could use all 5 points. It's really up to you, but you really only need 3 points to graph this. Okay. Again, the domain of a log function here, remember what we're taking the log of, whatever is plugged into the logarithm, needs to be greater than 0. It can't equal 0, it must be greater than 0. Okay. So we can also transform logarithms just like we do every other function we've looked at, the shifting up, down, left, right, all of that. And this is kind of the summary of that chart. It works exactly the same. The vertical and horizontal shifts here, if we have something added onto the end, it moves up, minus on the end moves down, added inside moves left, and then minus inside moves right, and then negatives can reflect. Constants multiplied outside or inside can stretch and shrink. So let's do some examples here. So we have log base 3 of x, which we just graphed on the previous page. And so if my base is 3, I'm going to use 1/3, 1, and 3. Plugging in 1/3 is going to give me negative 1. Plugging in 1 is going to give me 0. Plugging in 3 is going to give me 1. So 1/3, negative 1. 1, 0, and 3, 1. And then this shift here, minus 1 on the inside moves right, 1, and then plus 2 on the end moves up, 2. So each point moves to the right 1 and up 2, right 1 and up 2, right 1 and up 2. And if you think about your asymptote, moving up and down doesn't change a vertical asymptote, but moving to the right does. So moving it to the right 1 changes my vertical asymptote. And there is g of x. Okay. All right. And for a couple more examples here, we have negative log base 3 of x. So same graph that we just did, but the negative version of it. And how that changes the values I get. I'm still going to plug in the same values. I'm still going to plug in 1/3, 1, and 3. And for 1/3, I usually got -1, but times a negative becomes +1. Plugging in 1, I got 0, and 0 times a negative is still 0. Plugging in 3, I got +1, but times a negative will be -1. So this is reflecting it across the x-axis. So 1/3, I get 1, 1, 0, and then 3, -1. So instead of it going like this, now it goes like this. And I probably shouldn't have actually drawn that graph. We want to graph the shifting of it. This -2 moves me to the right 2. And so that also moves my vertical asymptote to the right 2. So now it's at x equals 2. Okay. So each of these points moves to the right 2. And that gives me my function g of x. All right, a couple more examples here. We're going to be graphing 2 log base 4 of x. And then shifting it, this -3 will move it down 3. So base 4 means I'm going to be using 1/4, 1, and 4. Plugging in 1/4, I would get -1. -1 times 2 is -2. Plugging in 1, I would get 0. 0 times 2 is still 0. Plugging in 4, I would get 1 times 2 would be 2. So that factor of 2 multiplies our outputs by 2. So 1/4 and -2, 1, 0, and then 4, 2. And then this -3 on the end moves it down 3, which does not change my vertical asymptote. It's still at the y-axis. But all of these points are moving down 3. Okay, and that is g of x. One more example here. And here it does not give you the parent graph, so you can still, even if it doesn't give you to graph the parent graph first, you can still use that to plot those points and then move them. This +1 in here moves me left 1. And I'm going to use 3 log base 2 of x. So I'll use 1/2, 1, and 2. Plugging in 1/2, 1/2 would give me -1, times 3 would give me -3. Plugging in 1 would give me 0, times 3 is still 0. Plugging in 2 would give me 1, times 3 would be 3. So 1/2, -3, 1, 0, and then 2, 3. So you can see it stretches it, makes it really steep here. And then moving left 1 moves my vertical asymptote left 1, so it's at x equals -1 now. And then all of those points are going to move left 1. And so that is the graph of f of x. So that's a few examples of logarithmic graphs. And that is the end of video part 8.